In 5, 4, 3, 2, 1. Welcome to Radioflash, Armada's podcast dedicated to defence and security in the electromagnetic spectrum, with your host Tom Withington at the controls. Now, they can be your best friend, they can be forever, be as big as the Ritz, you can even have them on the soles of your shoes. Diamonds have been around for almost 1 billion years and they're finding their way into defence applications. This tough carbon tolerates eye-watering levels of heat-holding promise for electronic warfare, radar and communications. But how might diamonds be used in these technologies and what makes them uniquely suited? Well, to discuss these questions today, we're joined from Oxfordshire in central England by Ian Friel, Element 6's Business Development Programme Manager, and Andrew Edmonds, Principal Scientist. Gentlemen, welcome to Radio Flash.
Thank you very much. Hi, everyone.
Thanks, Tom. Great to be with you.
Let's start by talking about the use of diamonds in defence electronics. So we know that they're used for cutting, for precision tool applications, for that kind of thing, for jewellery, obviously, perhaps most famously. But how are they being used in defence electronics?
The reason why diamonds are of interest is it has the highest thermal conductivity of any solid material. So you can achieve thermal conductivities greater than 2,200 watts per meter Kelvin at room temperature. So that's greater than 5 times that of copper. And at Element 6, we actually make a range of diamond heat spreaders with thermal conductivities that go all the way from 1,000 to 2,200 watts per meter Kelvin. And so we can tailor the heat spreader to the specific needs of our defense customers and other industrial customers. We can also supply them metallized in order to sort of facilitate integration into the device package.
We've talked a little bit about the sort of unique attributes of diamonds in defense electronics, but more specifically, how can diamonds be used in those defense systems that are actually working in the electromagnetic spectrum?
I'd say for applications such as electronic warfare, radar, military communications, at the heart of all these applications are devices called power amplifiers. So these are devices which emit very high power RF or microwave energy. So in an EW application, that energy might be used, say, to interfere with an enemy's defense systems. In radar, you're using microwave energy to locate objects at a distance. In military communications, you're using microwave frequencies for wireless communications. So I think very simply put, the more power that you can operate the power amplifiers in these applications, the more effective these applications are. And the problem with current sort of state-of-the-art solid-state power amplifiers is they're starting to hit power limits due to thermal management challenges. And so this is where diamond heat spreaders can and do play a role in improving the thermal performance of the package and therefore enabling greater microwave power in these devices. So as well as these kind of active RF and microwave devices, microwave circuits in these applications also require passive devices like resistors, terminators to absorb power, and diamonds also used in these passive devices as well. So diamond substrates allow you to basically scale the device down in size because of their ability to get the heat out in small areas. And what that enables you to do is operate at much higher frequencies before parasitic effects start coming in, which can distort the signal. And so reach higher frequencies that other thermal management materials just would not be able to achieve.
Well, I think it's also interesting to note there is interest in making active devices with diamonds. So when we talk about active devices, we're obviously having to then dope the diamond with different materials to actually make it a semiconductor. Now, there are a number of outstanding challenges with diamond that are still being actively being developed as we speak, and that involves revolves around doping the diamond with suitable dopants and getting the performance you need. Now, long ago, it was sort of ascertained and demonstrated that you could make a good p-type semiconductor with diamond by doping it with boron, but unfortunately nature is a little bit cruel when it comes to suitable n-type dopants for diamond. Nitrogen is the obvious candidate, but you actually end up with a very deep donor, so in practice those devices are not usable, whereas phosphorus has also been looked at to dope the diamond for generating those n-type semiconductors. But the challenge there is really getting phosphorus in with sufficient concentrations whilst not degrading the performance and abilities of the material. So that's still an area that is actively being worked on. The other important thing to emphasize is thermal management applications that Ian has been talking about. Polycrystalline diamond is suitable for those applications. But when we start talking about active electronic devices from diamond, we really need single crystal diamond. And that's an area, again, that we're actively developing, in this case, through our involvement in a DARPA proposal called Lattice. So watch this space.
Diamonds have been touted as a useful component for quantum communications. And I was wondering if you can explain to our listeners a little bit about why diamonds are so useful for this emerging quantum communications technology.
It's important actually that we appreciate that when we talk about applications with diamond where we're exploiting quantum properties, it's actually broader than just communication. Now, communication is one of those truly quantum applications where we're essentially using individual defects in diamond material to send information in a way that is protected by the laws of quantum physics. And as people might be aware, essentially there is this concept in quantum communication or quantum physics in general, whereby once you measure the state of something, you change it. So what that means is you can send information in such a way that you can sense if somebody is eavesdropping. Now, at the heart of those applications in diamond is the fact that we can actually create in demand particular defects in diamond which can act as those single qubits, so single pieces of quantum information. And the two candidates for that are known as the nitrogen vacancy and silicon vacancy. Now, quantum communication is perhaps one of the less mature areas when you look at using quantum enabled applications with diamond. The area that is much more mature is actually in the area of quantum sensing. So you can use defects such as nitrogen vacancy to build very sensitive probes of magnetic fields. And that's an area where there are companies now actively deploying prototypes in the field to actually test to see what diamond-enabled magnetometry can do. And there's a number of interesting areas that people are looking at there, one of which is around denied GPS navigation. So we're all obviously aware of GPS and our reliance on it, but it's not a technology that we can necessarily 100% depend on. There are a number of scenarios where you might not have access to GPS in a defense situation. It might be being jammed, or you might be underground. So for that reason, people are an industry very interested in looking at alternative sensors which don't have those jammings or denial of service issues. Now, because diamond can be transformed into a sensitive probe of magnetic field, and because people have built up very detailed maps of how the Earth's magnetic field varies from point to point, you can potentially use a diamond magnetometer to make a very good guess as to where you are on the Earth with knowledge of where you were previously.
When do you think we might start to see diamonds being used en masse for some of the technologies and applications that we've been discussing?
Happy to start with the heat spreader applications. That's actually already happening and has been happening for some time. So it's a fairly mature technology. We provided many CVD diamond heat spreaders for silicon and gallium nitride based devices. for many years, and it's a growing market for element 6. In terms of the active diamond electronic devices that Andy mentioned, it's difficult to say. There are some technical hurdles that need to be overcome, as Andy mentioned, and that's the motivation for programs like Lattice. But very difficult to say. It could be maybe 5 years before some commercial devices start appearing.
We always work with partners to actually produce devices. So I think you might get a slightly different answer from them, but I'd be happy to say sort of TRL4 at least, because there are prototypes that have been developed and tested, and this specifically is talking around the GPS denied navigation topic. As mentioned, broadly speaking, when you look at exploiting quantum properties of defects in diamond, it's a broad spectrum of TRL readiness, technology readiness levels. You've got devices that are measuring magnetic fields across test structures with devices available now. Essentially, people have built nice microscope systems where you are able to measure magnetic fields across test samples now. So it does depend a little bit on exactly which quantum sensing application we're referring to. But back to denied GPS navigation, you have got companies like Lockheed Martin who have been working on this technology and have been public with that, with demonstration devices. And there are other companies we're working with in the very closely related application of geosurveying, where they're looking to build up those maps of how the Earth's magnetic field varies. And again, they are at the stage of building test devices.
It's been fascinating talking to you both. I think this is going to be a technology we're going to be very keen to keep an eye on at Armada. So perhaps come back and have another chat with us again in the future. Let us know where you're getting to with the important research and work that you're both doing. But in the meantime, thank you both very much for joining us.
Thank you. It's been a pleasure.
Thanks for having us.
If you'd like to learn more about Element 6, why not visit their website at e6.com? And don't forget, there's more defense electromagnetic news and analysis at armadainternational.com. That's all we've got time for. Thanks very much for listening.